Welcome back to Algebra 1 with Miss Betsy. Today we're going to be doing a lesson that is pretty straightforward. It's actually quite amazing the length that they go through to try and explain this in your text. I'm going to take the time to walk through some of it, but we've been talking about combining like terms pretty much all year so far, and I'm hopeful that this will simply be another opportunity for you to have a relatively easy section of homework because you're already familiar to large measure with what you're doing. If you are just kicking into these videos and wondering what text I'm using, this is it. It's the second edition of Algebra 1 published by Bob Jones University Press. We are in section 3.5 on page 99. You can use any textbook, but in order to follow along with me exactly, I'm using the second edition. So let's pray. I have a lame joke for you, and we'll see how long it takes to get through this teaching. God, thank you that you are with us always. I ask that you would help us to focus on our studies today, regardless of what time it is or what's going on around us, or if we wish to be playing or doing something else. Help us to be diligent to do those things that you have placed before us right now. Help me to communicate and help the kids and parents to understand. I thank you for that in the name of Jesus. Amen. Okay, lame joke. Now, what do you call a sleeping bull? What do you call a sleeping bull? Well, that would be a bulldozer. Sleeping bull is a bulldozer. Now, anytime we're expressing answers or quantities or coming up with a solution, not just in algebra or just in arithmetic or any math class, we always want to have that answer expressed in the simplest form possible. So let's say that I'm talking to you and I'm telling you about the fruit I have. And I tell you that I have 11 apples and I have 6 oranges and I have 5 apples. How many of us would actually talk about that? I mean, unless we just really were specific about the types of apples we had. Maybe I'd say that I had 11 Fuji apples and 8 oranges and 5 Granny Smith apples, because then it would be perhaps relevant. I've got red apples and I have green apples. But we're not typically going to say 11 apples, I'm losing my illustration, 11 apples, 8 oranges, and 5 apples. We're going to say 11 apples plus these 5 apples over here. I'm going to put them all together in one group, and that's going to be 16 apples. And that is what we are talking about when we refer to something called a like term. And these are not that you like somebody on Facebook or that you unlike them or you friend something or you unfriend it. Like terms are simply terms, let me see. Like terms simply have the same variable and they have the same exponent. And this is essential that you know this. Like terms have the same variable and the same exponent. Only. Now the coefficient does not have to be the same. And you say, what's the coefficient? The coefficient's the number that comes in front, like 2x. The variable is x. The coefficient is 2. It's the numerical part of that algebraic expression. And a term can be, it's a constant. This can be a term. It's a variable. It can be an expression including a coefficient and a couple of different variables. There are 3 terms here. 4 is a term, x is a term, and 2xy squared is a term. Terms are going to be separated by addition signs or by subtraction signs. We could have had something that looked like that. 4 minus x plus 2y. Something that's important to remember about terms is that the sign in front of them goes along with this. If we have a negative x, If we don't have a number in front of that variable, we understand that we're talking about a 1. So we have a negative 1x, we have a positive 2xy squared. And it's important, it's essential that you realize that the signs go along with them, just like this is a positive 4. Because when you collect like terms, you're going to be adding or subtracting according to the sign in front of that term. So let's say that we have an expression, actually they've got a different expression in the book they're talking about, but here we have a 3-term expression, 4 negative x and 2xy squared, and theirs was 3x minus 4y plus 5x. 3x minus 4y plus 5x. How many terms do we have here? Well, we have 3 terms because they are separated. The 3x is separated from the 4y by a minus sign. The negative 4y is subtracted from 5x, separated from 5x, I'm sorry, by an addition sign. So we have 3 terms. We have 2 terms that are like terms. We have the 3x and we have the 5x. Okay? Positive 3, positive 5x. And they're like terms because we said they have to have the same variable, which is the x, and they have to have the same exponent. There's no exponent visible here, so we know that the exponent is 1. This is very similar to the illustration that I opened this lecture up with when I said 11 bananas, 5 oranges, and 6 apples. This is like saying 3 apples minus 4 bananas plus 8 apples. 3 apples and 8 apples, and that 8 was the answer. 3 apples minus 4 bananas plus 5 apples. 3 apples and 5 apples is 8 apples. 3x plus 5x gives us a value. These are like terms, so we add them together, and that becomes 8x. So we have 8x minus 4y. So what do you do to combine like terms? You keep the term, you keep the variable, which is x, and you add or subtract the coefficients. Remember, the coefficient is the number in front of the variable. 3x minus 4y plus 5x. In simplest form, we combine the like terms to get 8x minus 4y. Now there's nothing else that we can do. So let's move on and see what we're talking about on page 100. They have a definition at the top of the page about what a numerical coefficient is. It's the numerical factor or a constant accompanying the variables in a term. The coefficient is the number plus the sign that is in front of these variables. This coefficient is 3. The coefficient here is a negative 4. This is a positive 5. This coefficient is 2. The coefficient here is a negative 1. This 4 is not a coefficient, it's a constant term. It's called a constant. And that's because 4 is always equal to 4, because it's not ever going to change. This negative x could be negative 100, negative 2.73, negative 8/10. It's going to be a variable. It's going to vary because it has that letter in it that says, okay, what value am I going to have to assign to x? So there are only 5 coefficients here because we only have 5 terms that have variables. This is a constant. Coefficient is negative 1. Coefficient is positive 2, positive 3, negative 4 is the coefficient here, and positive 5 is the coefficient. And they continue to make a point that when you work with like terms, you're actually applying the distributive property in reverse. I've tried to illustrate that for you in previous videos. I've tried to teach it to you. It's a little bit of technical theory that I'm not making that a hill to die on, as long as you understand that to combine like terms, you add the numbers in front of them. Add or subtract the numbers in front of them. You have to know that like terms have the same variable, the same coefficient, and you have to know that that number that's in front of the letter is what we call the coefficient. So let's go ahead and look at their examples here on page 100. Example 1 says, combine 3x plus 5x and it says use the distributive property in reverse. I don't honestly care if you use the distributive property in reverse. If you chose to do that, the distributive property in reverse would say that's going to be 3 plus 5 times x, which gives you 8x. Remember what our distributive property is? It tells us that if you have something that looks like this, a times the quantity b plus c, that's the same as a times b plus a times c. So what we have right here is a times the quantity b plus c is the same as a times b plus a times c. So this is the math theory behind how you combine like terms. This is the distributive property. You must understand the distributive property because you will use it all the time. It's enough for me for you to know that if it says combine 3x plus 5x, we've got our common variable. The x, these are like terms. We're simply going to add the exponents. I can't believe I said exponents. We're going to add the coefficients. 3 plus 5 gives us 8. So the simplest form of this expression, 3x plus 5x, is 8x. All right? Example number 2 says, simplify 3x plus 4y minus 5x. This is example 2. 3x plus 4y minus 5x. And what I'm going to do here is I'm going to rearrange these terms so that I put all of the same variables together so that I'm collecting like terms. I'm allowed to do this because the commutative property tells us that you can change the order of terms without changing the value of that equation. So just so that you know what I'm doing, I'm going to write out here alongside of it that I'm using the commutative property as justification or as permission to move these around. Now you see that I have two terms in the front that are like terms. 3x and a negative 5x. We have to add together a 3 and a negative 5 gives us a negative 2x plus 4y. And that right there is all there is to do. You can't say, well, negative 2x plus 4y is equal to 17, because you don't know what that value is, because you haven't been given numbers to substitute in here for x and y. Now, in your book, they've got an extra step in here where you're applying the distributive property in reverse. I'm going on the assumption that you've learned or are learning right now that the way you combine like terms is by adding or subtracting the coefficients as necessary. So that was example 2. See what we have here for example number 3. And I've got 2 of my markers that are uncapped at the same time, which is never a good idea. Let me see if I can rescue this black one over here as I erase the board. Example number 3 at the bottom of page 100 tells us to simplify 7x squared plus 8x minus 4x squared plus 10x. Now, do I have any like terms here? Do I have 1, 2, 3, 4? Do I add all of these together? No. I have two pairs of like terms. I have 7x squared, negative 4x squared. And then I have positive 8x and positive 10x. And you say, but they're all x's. Yes, the variables are all the same. But in order for them to be like terms, they have to have the same exponent as well. We have a square here. That's why 7x squared and a negative 4x squared are the like terms. So I'm going to use my, it's justified by my commutative property that lets me change the order of these terms so that I have the x squareds and then the x. And we've talked in the past of like math syntax, like you have grammar, or math grammar, like English grammar. You have rules as to how you put together a sentence. We do that same thing in math. When we have the same variable, we're going to arrange them in descending order of variable, which means that we're going to go the highest variables first. 7 minus 4 is a positive 3x squared, plus 8 plus 10 is plus 18x. That's all that's involved in simplifying this problem. Once you get to where you have no more like terms, you're finished. There's nothing else you can do at this point. Let's go ahead and look now at the top of page 101. It says, how do you combine like terms? First you find all of the like terms. That would be duh. X squareds are the same, and the x's are the same. So I have two, and yet again more proof of why I don't teach art. We have two pairs of like terms. Now it says combine the like terms by adding the coefficients. Adding the coefficients, you say, oh, but it's subtraction. Remember, subtraction is the same as adding the opposite. 7 plus a negative 4 is 3. 8 plus 10 is 18. So that's how we arrived at those answers. Now let's look at example number 4. I'm going to go ahead and erase our definition of like terms because by now I expect you to completely understand what like terms are. Example 4 says simplify 2x plus 4y minus 8x plus 3z minus 5y. Guys, don't just come up with the answer from here. I know that you can do it, but if you will at least take an extra step and group your like terms together. Now we don't have any we don't have any exponents here to worry about. We simply have variables. How are we going to know what comes first? You know, we naturally count 1, 2, 3, 4, 5. We naturally say A, B, C, D, E, F, G. We don't go A, Z, Q, R, T, U, S, T, M. Okay, let's put the letters in alphabetical order. So our first terms are going to be the x's. 2x minus 8x plus 4y minus 5y plus 3z. And this just makes it easy to keep up with what you're doing. We have our x's, our like terms. 2 minus 8, or 2 plus a negative 8 is a negative 6x. Plus, we have two y terms. Positive 4 minus 5 is plus a negative y, or minus y, plus 3z. That is all that's involved in simplifying this expression. There's nothing else that you can do. All right, now, example 5. They have like tons of examples in this book, and I am getting so dry. So I think I better get a drink. Trusty water glass here. Okay. Number 6, simplify 8x cubed minus x squared plus x cubed plus 4x cubed minus x squared plus 6x cubed. Can you see that there might be value, particularly here, to taking the time to go back and make sure that you've copied all of your expressions properly? Yeah. 8x cubed minus x squared plus x cubed plus 4x cubed minus x squared plus x cubed. What do you have that are common? You have cubes and squares. 8x cubed plus x cubed plus 4x cubed minus x squared plus, 6x cubed. I missed one, didn't I? So I'm going to group them together. Let me make sure I've got x cubed, 8x cubed plus x cubed. See what I did? You think maybe I'm doing this on purpose to show you how important it is? 4x cubed, what did I write? I wrote 4x squared, 4x cubed, minus x squared, plus 6x cubed. I've got this puppy over here I need to not forget. So I have 4x cubes. 8 plus 1 is 9, plus 4 is 13, plus 6 is 19x cubed. See, now I don't trust myself. 19x cubed, negative 1 plus a negative 1 is a negative 2x squared. That's all they're talking about. I think what they want you to see here is that you've just got a long string of numbers. Make sure you keep your exponents available and don't trip up into this and say that the answer is just 19x cubed, because there's no number here. If you don't have a visible number in front of your variable, if you cannot see what that coefficient is, it's understood to be a 1. So we have negative 1 minus 1 is a negative 2, or negative 1 plus, minus 2 addition is the same as adding the opposite, so it would be negative 1 plus another negative 1 gives us a negative 2x squared. Alright, let me do one more example. This is example number 7. And you will have an occasional problem that is very, very similar to this. Simplify 2x squared y plus xy squared plus 4x squared y z minus 3x y z. Alright? 2x squared y plus xy squared plus 4x squared yz plus 3xyz. How many like terms do I have here? Well, we've got these two right here, correct? No, we don't. You've got to be very cautious. We have an x and a y, and we have a square, but a different variable is squared. This is x squared, and here we have y squared. Like terms have to have the same variable and the same exponent paired together with the same variable. So we have one square and one square here, but they're not matched up with the proper variable. So these are not like terms, and these are not like terms either, because we have x squared and we have x. So there's nothing else that you can do. This is already simplified. Be very careful, because you will find that more often than you tend to think, something like this right here is going to trip you up, and I don't want you to do that. So be very careful to pay attention to the detail of like terms, that not only Do the variables have to be the same? The exponents have to match, but the exponents have to match with the specific variable. In order for this to be like terms, it would have had to have been x squared y. Xy squared is a completely different animal altogether. Go ahead and play around with these. Do your best to get every single one of them done. Go back, check your work. If you're stuck, send me a text. If we really want to talk about it, we can illustrate it more in class on Friday.